this episode, we build directly on identity abuse and focus on what often comes next: lateral movement. Once an attacker gains a foothold in a cloud environment, whether through a compromised identity or a vulnerable workload, they rarely stop at that first point of access. Instead, they look for ways to move sideways, reaching additional systems, escalating influence, and expanding control. Lateral movement is dangerous because it turns a small breach into a broad compromise, and in the cloud it can happen quietly through legitimate service calls and internal connections. The key to detecting it is understanding how normal communication paths look and then spotting the relationships that do not belong. By the end of this discussion, you should be able to explain how monitoring network flows, service-to-service activity, and unexpected access paths helps reveal attacker pivot behavior before it spreads too far. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. Lateral movement simply means moving from one resource to another inside the same environment. In a physical building analogy, it is the difference between breaking in through a window and then walking from room to room, unlocking additional doors. In cloud environments, those rooms might be virtual machines, containers, databases, storage services, or management interfaces. The attacker's goal is often to find higher-value targets, such as systems that store sensitive data or identities with broader permissions. They may also seek persistence, ensuring that even if one access path is closed, others remain open. Because cloud environments are highly interconnected, lateral movement does not always require exploiting new vulnerabilities. Sometimes it just requires using existing trust relationships in unexpected ways. That is why detection depends on understanding how systems are supposed to talk to each other. Network flow data remains one of the strongest signals for detecting lateral movement because it shows who connected to whom and when. Flow logs capture metadata such as source address, destination address, ports, protocol, and sometimes byte counts and duration. Even without seeing the content of the traffic, you can map communication patterns across workloads and services. In a well-designed environment, most workloads have predictable communication partners, like a web tier that talks to an application tier and an application tier that talks to a database tier. When a workload suddenly initiates connections to multiple internal systems that it has never contacted before, that shift can indicate reconnaissance or pivoting. Flow patterns also reveal directionality, which matters because many systems are designed primarily to receive connections rather than initiate them. When the direction flips unexpectedly, it is worth investigating. Service-to-service calls add another layer because in cloud architectures, much lateral movement happens through application interfaces rather than raw network ports. Modern systems rely heavily on APIs, internal endpoints, and message queues, which can all become pathways for pivoting. Monitoring service call logs helps you see which identity or workload invoked which API and whether that pattern is typical. For example, if a backend service that normally only reads data suddenly starts calling administrative APIs to modify configurations, that is suspicious. Attackers may use stolen credentials to call legitimate APIs that allow them to enumerate resources, attach permissions, or access sensitive data. These actions may not look like traditional hacking, but rather like normal operational commands used in the wrong context. Correlating service calls with network flow changes strengthens detection because it shows both the connectivity and the intent. Unusual access paths are often the clearest indicator of lateral movement, but only if you understand the expected architecture. An access path is the sequence of trust relationships and network routes that allow one entity to reach another. In a properly segmented environment, certain systems should not be able to talk directly to others without passing through defined boundaries. When a workload bypasses expected boundaries or uses an indirect route to reach a sensitive resource, that can indicate compromise. For instance, if a development environment suddenly accesses a production database directly, that breaks architectural expectations. Attackers often look for these unexpected paths because they represent weak points in segmentation. Monitoring for deviations from approved access paths requires you to know not just what is possible, but what is intended. Baseline modeling is critical in lateral movement detection because cloud environments are dynamic. New instances spin up, containers are deployed and terminated, and services scale automatically. Despite this dynamism, certain relationships remain relatively stable, such as which services depend on which databases or which workloads require outbound internet access. By observing normal patterns over time, you can build a mental or documented map of expected connections. When lateral movement begins, it often introduces new edges in that map, like connections between nodes that previously had no relationship. Detecting new or rare connections is therefore a practical strategy, especially when those connections involve high-value targets. Baselines do not need to be perfect. They need to be good enough to flag meaningful deviations. Attackers often perform internal reconnaissance before fully committing to lateral movement, and flow data can expose that reconnaissance phase. You might see a compromised workload attempting connections to many internal addresses on various ports, looking for responsive services. Even if most attempts fail, the pattern of scanning is distinct from normal application traffic, which is usually targeted and predictable. A sudden spike in connection attempts across multiple internal destinations can indicate mapping activity. Combined with identity logs, you may see the same identity performing resource listing operations through cloud APIs. The combination of internal probing and API enumeration strongly suggests exploration beyond normal use. Catching reconnaissance early can prevent the attacker from identifying more valuable targets. Privilege boundaries are also relevant to lateral movement because movement is often constrained by permissions. An attacker who compromises a low-privileged workload may try to access other workloads that share the same role or security group. Monitoring should therefore pay attention to access attempts across permission boundaries, especially when denied attempts cluster together. Repeated denied connections can be as informative as successful ones because they reveal intent. If a workload repeatedly attempts to connect to a database it is not authorized to access, that may indicate pivot attempts. Denied API calls that seek elevated roles or restricted resources also reveal probing behavior. Observing both successful and failed attempts provides a fuller picture of lateral exploration. Internal authentication events can further illuminate lateral movement. When a workload initiates connections to another service, it often authenticates using a service identity or token. If that identity is used from a new source workload, it may indicate credential theft or misuse. For example, if a service account normally authenticates only from one application server but suddenly appears from a different host, that is suspicious. Correlating flow data with authentication logs helps confirm whether a connection represents authorized behavior. This approach connects identity abuse and lateral movement detection, reinforcing that the two are deeply intertwined. By mapping identities to source systems and comparing against expected patterns, you reduce the attacker's ability to pivot unnoticed. Another important aspect is timing and sequence. Lateral movement often follows a compromise event, such as a suspicious login or a privilege escalation. Monitoring systems should be able to connect these dots, recognizing when new internal connections begin shortly after a risky identity event. If a compromised account authenticates, and within minutes the associated workload begins contacting additional internal services, that temporal proximity increases suspicion. Even slower movements can be detected by observing gradual expansion of connections over days or weeks. Sequence-based analysis, rather than isolated alerts, helps you see campaigns rather than single anomalies. The attacker's journey is usually a chain, and detection improves when you reconstruct that chain. False positives remain a challenge, especially in environments where deployments and scaling events introduce legitimate changes in connectivity. To reduce noise, monitoring should incorporate context such as deployment records, configuration changes, and known architectural updates. If a new service was intentionally deployed and begins communicating with expected dependencies, that should not trigger alarm. However, if a stable workload with no recent change suddenly initiates new connections to sensitive systems, that warrants attention. Combining architectural knowledge with flow and service logs refines detection accuracy. The goal is not to alert on every new connection, but to alert on new connections that violate trust expectations. Investigation of suspected lateral movement benefits from visualizing relationships. Graph-based views of connectivity can show clusters of normal communication and highlight new edges introduced by compromise. Even without sophisticated tooling, structured log queries that group connections by source and destination can reveal expansion patterns. Investigators should ask whether the source workload was expected to initiate such traffic and whether the destination was designed to accept it. They should also examine whether permissions or network rules were modified shortly before the connections began. These questions tie back to identity monitoring and control plane activity, reinforcing the importance of cross-domain correlation. Effective investigation depends on having collected the right signals in the first place. Ultimately, detecting lateral movement in the cloud is about recognizing when systems interact in ways that break architectural intent. Network flows show the raw movement, service calls reveal operational intent, and unusual access paths expose segmentation failures. By baselining expected communication patterns and correlating changes with identity events, you can detect pivot behavior before it spreads across the environment. Lateral movement thrives in environments where internal trust is broad and visibility is shallow, but strong monitoring narrows those blind spots. When you think of the cloud as a map of relationships rather than a flat space of traffic, movement becomes easier to see. That perspective prepares you to detect the final objective many attackers pursue after moving laterally, which is the exfiltration of sensitive data or the establishment of durable persistence.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit BareMetalCyber.com.